Hello, this is the second part of Chapter 3, Fundamentals of Crystallography. After finding a vector in hexagonal crystal with a given crystallographic direction, now we do vice versa. We are given a vector in hexagonal crystal structure and we are asked to find its crystallographic direction. First, we determine coordinates of vector tail, which is point 1, x1, y1, and z1, and vector head, which we call it as point 2, x2, y2, and z2, in terms of three axes. By three axes, I mean a1, a2, and z. In the second step, we subtract tail point coordinates from head point coordinates and normalize it by unit cell dimensions, which is here a and c along direction z. The third step is adjusting to smallest integer value. By smallest integer value, we mean that we exclude the value 0, and then we find the smallest value among the rest, and we multiply it so that the smallest value become unit or become 1. Of course, the rest gonna be bigger than 1. Next step now is to enclose these values, as you can see here, as u prime, v prime, w prime. And then using these relation, we can find the value of u, v, t, and w. Again, for u, v, t, w, we adjust it to smallest integers, so whichever among u, t, and w are smallest, we make it 1, and then of course excluding 0, and then of course the rest is going to be higher than 1, and we add a bracket that has 4 components. This one is our HCP crystallographic direction. And now let's solve an example. We want to find hexagonal crystallographic directions for the green vector as shown here. Regenerating from 0, the origin, to this point. So the first step is to determine the coordinates for vector, head and tail. Of course, for origin we have 0, 0, 0. This is origin. For this point, if we project this one along a1 axis, of course the value along a1 gonna be 1 unit, and or equal to a, the same as these sides. And if we project it along a2, it's gonna be the same value as a. So we have, this is the value of tail location, head location, so a, and of course there is no change along z direction. Next step is we normalize it based on these parameters a and c. A and c are unit cell dimensions, so it gives us 1, 1, 0. And after that, we do what we do is to reduce. So here, because if we exclude 0, this value is already 1, so in the reduction we don't see any change. Therefore, these terms are making our u prime, v prime, and of course w prime, as you can see here. So we leave it in the bracket. So as I said, the next step is to find the values of u, v, t, and w, as you can see here. If we plug these values of u prime, v prime, and w prime, we have these values for u, v, t, and w. The next step is reduction. So we have these values 1 over 3, 1 over 3, minus 2 over 3, and 0. So as I said, for reduction, we exclude the value of 0. We look at the smallest absolute number, which is 1 over 3. We make it 1. How? By multiplying it by 3. So this one gonna be 1, this one gonna be 1, and this one gonna be -2 and 0. So we have these 4 value, and then we enclose everything inside this bracket, and this is showing our HTTP crystallographic direction. The orientation of planes for crystal structure are presented in a similar manner to what we did for crystal directions, what we presented before. Again, the unit cell here is the basis. So the unit cell, as you can see here, and we have 3 axes coordinate system similar to what is presented for general crystal structure. In all crystal systems, except for hexagonal one, the crystallographic planes are specified by 3 numbers HKL inside the parentheses. We know these as Miller indices. So these are, as an example, called Miller indices for this group of planes. Why do we need Miller indices? Later you will see that we need to know the indices to be able to address different features and crystal features like grain boundaries and twinnings. This will be discussed in chapter 9. All parallel planes, as you can see here, like these three or these three, they have similar Miller indices, and the process is as follows. First of all, if the plane is passing through the origin, so something like this, it's passing through origin, then we have to make it either parallel plane at reasonable distance within unit cell, or we have to move origin again or translate origin so that we can establish another unit cell. We will work so that we can establish another unit cell. We will work on similar example in class. Okay, to find the Miller indices, first we have to find where these planes intersect with the axis X, Y, and Z in terms of A, B, and C. Of course, if the plane is parallel to one of the axes, this value will be infinity. After that, we have to find reciprocals of the values found in step 1. Of course, for parallel case, the reciprocal gonna be 1 over infinity, which is 0. So we will have 3 reciprocals. These 3 numbers then are changed to the smallest integer value. We have to multiply or divide them with the common factor. And just remember that do not confuse this with direction that we don't take reciprocals. As an example for reduction, if we end up with these 3 values for reciprocal 2, 0, 0, 0. Of course, these values are already 0 and they are all integer values. We are fine, but we are looking for the smallest integer value. So if we divide all of them by 2, these 2 will remain 0 and this one will be 1. Of course, this is the smallest integer value for these 3 numbers. But if we have a value like this one, 5, 2, 0. Of course, if we divide these by 2, this gonna stay still 1 as integer, this will be integer, but this one is no more integer, so we'll leave it as is. Another example can be similar to this one. If we have values of 1 over 3, 1, and -3 over 4, how we can make it into smallest integer values? That's your task to do it in the class. You can also find more directions and also examples in the following link. Let's look at more examples here. We want to find the crystallographic planes or the Miller indices for this blue plane shown here in the cubic unit cell. The first thing is to find the intersection of this plane with X, Y, and Z. As you can see, it intersects with X at point A, or 1, with Y point B, or again 1 in terms of B, and it's parallel with Z-axis, which is infinity, as you can see here. The next step is to find reciprocal. Of course, this will remain as 1, 1, and this will be 0. And then we do reduction. Of course, this value don't need to be changed because we are dealing with the smallest integer value. And after that, we can enclose them in parentheses, and this is the Miller indices for this blue plane. Now look at this red plane, the cubic unit cell. As you can see here, again we look at the intercepts. With x, it's intersecting at half. With b, it's parallel. With c is parallel. So these two gonna be infinity, and this is half. We do reciprocal, so this is gonna be 2, 0, 0. And the next step is reduction. Of course, if we divide these by 2, these 2 remains integer, and this one will be reduced to a smaller integer, which is 1. And of course, now we can enclose them in parentheses and call it the Miller indices for the current red plane. This is another example. Look at this red plane here and the cubic unit cell, and it's intersecting with different axes. As you can see here, we look at the intercepts. It intersects with x-axis at 1/2, with y at 1, and with z at 3/4. The next step is to do reciprocals. This will give us 2, 1, and this is going to be 4/3. The next step is to do reduction. So before going to reduction, look at these 3 numbers. We want to make sure that all numbers are integer. This is already integer, this is integer, and this one is fraction. To change this one into an integer, the smallest integer, which is 1, we have to multiply everything by 3. So just do it. So this is going to be 6, this is going to be 3, and this is going to be 4. Of course, we cannot change this one, and we enclose all these 3 numbers in parentheses, and this is the Miller indices for this specific plane. And then now the question, what will happen if this plane or any plane passes through the origin? How we can find the Miller indices? We can work on this in the class. Apart from crystallographic, finding crystallographic planes, remember that in the cubic system, planes that have the same indices regardless of order or sign, they are equivalent and they belong to the same family. We show it as family of planes. As you can see here, these different planes actually belong to the same family. This is mainly because how atoms are located in different planes. In these different planes in a crystal are the same. So this is how we show it. We leave all these indices inside a curly bracket. We can have more practice using virtual material science and engineering prepared by Wiley. So I go to the proper chapter. So as you can see, we have different ones. So I click here, I go to chapter 3. I go down, click on the virtual material science and engineering. Click on material, crystal, and structure, and then look for crystallographic planes. As you can see, we have planes like this one, and you can explore in it. As you can see here, zoom in, zoom out, and you can play and look at these planes at different angles, similar to what you see here. For example, this one is 201, so on and so forth. Okay. How to find the Miller indices or crystallographic planes in hexagonal unit cell? It's presented here, and it follows the same procedure as cubic unit cell, what we went through it in cubic unit cell. And the only difference is that we here deal with 4 axes instead of 3 axes in cubic unit cell. So here we have A1, A2, A3 and also Z along C along Z axis. So the first step is to find intercepts with these three axes. As you can see, it intercepts with A1 at 1.1, with A2 is parallel, so it's going to be infinity, with A3 is actually intersecting at this point, which is -1, and with C it's actually crossing z-axis at 0.1. So we have these intercepts. The next step is to do reduction. Sorry, to find reciprocals. So we divide them, or we find them. The reciprocal as shown here. One gonna be 1, infinity will be 0, -1 the same, and 1 stays the same. The next step is to do reduction. As you can see, all of these numbers are in integer form, and they cannot be smaller than this one, so we leave it as is for the reduction part. And the last part is enclosing these numbers in parentheses and changing negative sign to a bar sign. So this is the Miller indices for this blue plane in HCP crystal. In this example, we are asked to find or to draw these two different planes. So now, based on what we went through, we can easily draw these planes. Later you will see that by knowing how many atoms in each of these planes, we can find the value of planar density of these ones. This will be discussed in the next chapter. Okay, in summary, as we discussed, we found when atoms are solidifying, they may assemble into crystalline or amorphous structure. Crystallographic points, directions, and planes are specified in terms of indexing schemes, so we talked about it and learned about it. Crystallographic directions and planes are related to atomic linear densities and planar density. This will be discussed more in the next chapter. And we also learned that materials can be single crystal or polycrystalline. Materials properties generally vary with single crystal orientation, but are generally non-directional in polycrystals. In polycrystals, they are non-directional with randomly oriented grains. A very good presentation of how atoms are solidifying and then they make a polycrystalline was created by Badr al-Ramadan. I posted the video here. You can look at the video using this link, and I will upload it to the model. Thank you.